So in the last video, we calculated surface area. So we had a surface parameterized by two variables, u and v, and we said the surface area was the integral over the surface of magnitude of partial derivative with respect to u cross partial derivative with respect to v, du dv. And that's analogous to our line integral, actually for calculating basically circumference. Those of you who tried or saw someone else present on the circumference of an ellipse, although much easier would be to calculate it for a circle, right? That was the integral over c of 1 ds, basically, probably little s, where you could replace ds with the magnitude of r prime of t dt. Okay, but we had other types of line integrals. We were able to actually integrate over c of any function of s, or of, let's write function of t. Well, I don't know. We'll write f ds. See, the notation is weird. And then we can write, and this was f plug in r of t. There we go. Magnitude of r prime of t dt. Right, this was any scalar function. So the same thing can be done with a surface integral. With any scalar function f, you can integrate over your surface. F of, now we're going to plug in whatever the parameterization of the surface is. So just like we stuck this in front and everything else was the same, we're going to do that here. We'll stick that here, and then everything else is the same. Ru cross Rv. Because this last thing is really just that replacing dA. Okay, so that's a scalar function. And then we were also able to integrate any vector field over the curve if we wanted to talk about work done in various directions. This was f dot dr, which was the integral over c of, we plugged in r of t. Now we had a vector function, vector field, dotted with r prime of t dt. Okay, we can do the same thing over a surface. We can integrate over the surface, and then we're going to have big F. We plug in the surface, the parameterized surface, but F is now a larger vector field, and then we're going to dot it with the cross product, which is a vector, and then integrate over u and v. And the difference here is that the curve is parameterized with one variable t, and the surface is parameterized with two variables, u and v. Okay, so why would you want these things? Surface area, self-explanatory why we want it. Function, this could be like a mass density function, for example. So if you have some surface and it's heavier in some places but lighter in other places, you want to find the total mass. You can now do that over a surface. Remember before we did it over a wire, where the density might change depending on where in the wire it was. Over here, we're actually going to start to calculate a thing called flux. And this is like, you have some surface here, and you're going to have water flowing through the surface. And maybe it's flowing faster in some places than others, and you want to calculate the total amount that's flowing through. So that's one example of flux. It's also used in, if you look at electric or magnetic fields, calculate flux all the time. Things that are going in and out of surfaces, and we'll talk about this later, but this is can't be calculated for all surfaces. We'll talk about which surfaces are allowed and which aren't. And we'll give lots of examples. So in the next several videos, I'm going to give a lot of examples of the scalar field surface integrals. This is necessarily hard, but we might still be getting a hang of parametrizing surfaces, and sometimes the math comes out a little weird. So I'm going to first do a bunch of videos with examples of this thing, and then we'll do a bunch of videos of examples of flux, and then we're going to get into Stokes' theorem, which might give us some easier ways of calculating flux.